There are monuments that survive because no one touches them. The Golden Gate Bridge survives for the opposite reason. Beneath the familiar orange towers, crews inspect steel, renew paint, replace worn parts, and prepare an 89-year-old structure for earthquakes its original builders could not fully model. We remember the bridge as a finished masterpiece from 1937. In reality, it has never been finished. Its beauty depends on endless work, much of it invisible, and that may be the real reason this bridge became more than a way across water. From end to end, the bridge stretches 1.7 miles, or 2.7 kilometers. Its main span runs 4,200 feet, 1,280 meters between two towers. Inside each main cable are 27,572 individual wires. Laid out in a single line, the wire in both cables would circle the Earth more than 3 times. Those numbers explain the scale. They do not explain the memory. Why did this bridge, among thousands, become instantly recognizable? Who truly shaped its design? What did workers risk to build it? And why must each generation quietly rebuild part of it? Before the bridge, the Golden Gate Strait was not an empty gap waiting for steel. It was the entrance to San Francisco Bay, a working channel used by ships, ferries, military installations, and communities on both shores. Travelers between San Francisco and Marin County depended on boats. By the late 1920s, ferry traffic was struggling to meet demand. Yet, the crossing remained difficult enough that many engineers considered a bridge too costly or simply impossible. The challenge was not only distance. It was deep water, strong currents, wind, navigation, and the seismic landscape of coastal California. The modern campaign began to take shape in 1916, when engineer and newspaper editor James H. Wilkins helped revive public interest in a fixed crossing. In 1919, San Francisco officials asked city engineer Michael O'Shaughnessy to investigate. Engineers consulted across the country often estimated a cost above $100 million and doubted the bridge could be built. Joseph Strauss answered differently. He argued that a crossing was feasible and proposed a much lower price. In 1921, he submitted a hybrid design part cantilever, part suspension bridge, and began years of public persuasion. The opposition was serious. Ferry interests fought a bridge that threatened their business. Shipping groups questioned whether the structure would obstruct navigation. Critics feared it would damage the natural setting, fail in an earthquake, or leave taxpayers responsible for an engineering disaster. Legal challenges and political resistance lasted for years. Supporters had to create a special public district, secure federal permission over a strategic harbor entrance, assemble counties behind the project, and defend a plan whose success depended on future toll revenue. Long before steel rose above the water, the bridge was a contest over risk. Then, the argument reached voters at the worst possible moment. On November 4th, 1930, as the Great Depression deepened, the 6-county bridge district asked for authority to issue $35 million in bonds. The taxable property of the district would stand behind them. Farms, homes, and businesses were part of the financial base for a bridge that did not yet exist. More than 145,000 people voted yes. Fewer than 47,000 voted no. It was not a federal monument handed down from Washington. It began as a regional gamble, approved by communities willing to carry the debt. Popular memory prefers a single heroic designer. The Golden Gate Bridge resists that story. Strauss was the chief engineer, public advocate, organizer, and political force who kept the project alive. But the final bridge emerged from a team. Consulting engineer Leon Moisseiff advanced the suspension concept that replaced Strauss's heavier hybrid proposal. Engineer Charles Alton Ellis directed thousands of calculations and prepared much of the technical design. Consulting engineers reviewed the work. architect Irving Morrow shaped the bridge's appearance. The icon was not one man's idea. It was collaboration unevenly credited. Ellis's role reveals the cost of the heroic myth. Trained as an engineer and mathematician, he spent years working through stresses, loads, specifications, and the immense calculations required before digital computers. Yet in late 1931, Strauss placed him on indefinite unpaid leave. Ellis continued working, and his contribution was not acknowledged on the original dedication plaque. Later bridge histories restored significant credit to him, but the omission endured for decades. The structure, celebrated as a triumph of modern engineering, also became a lesson in how public monuments can preserve a name while obscuring the labor behind it. The bridge might also have looked entirely different. Steel arriving from Eastern foundries carried a reddish primer. Irving Morrow recognized that the color worked with the hills while standing apart from sea and sky. His studies led to the specification now known as Golden Gate Bridge International Orange. Other schemes, including gray, were considered. The chosen color did more than protect an engineering work from visual anonymity. It gave the bridge a personality. Long before people saw the calculations, they saw the orange line. Over time, that color entered postcards, family photographs, home movies, and the visual language of California. Construction began on January 5, 1933. On the San Francisco side, the approach had to pass above Fort Point, a 19th century military fortification at the mouth of the bay. Rather than erase the older structure, the bridge crossed it on a great steel arch. The result joined two eras: masonry built for coastal defense and modern steel built for automobile movement. It was an early sign that the bridge would not stand outside history. It would absorb earlier landscapes, technologies, and institutions into a new route, while leaving enough of the old world visible beneath it. The work was difficult from the beginning. A temporary trestle extending from San Francisco into the strait was struck by a ship in 1933, then badly damaged again by a winter gale. Crews repaired it and continued. They built the South Pier in the water, raised towers 746 feet to 27 meters above their foundations, and prepared anchorages massive enough to receive the pull of the cables. The bridge was not assembled as a single rigid object. It grew through sequences: foundations, towers, catwalks, cables, suspenders, trusses, and finally the roadway hanging below. Its logic is elegant. The roadway loads move through vertical suspender ropes into the two main cables. Those cables pass over the towers and descend into enormous anchorages, which resist the pull at both ends. The towers carry forces downward into their foundations. Each main cable is more than 3 feet, about 92 centimeters in diameter. Its thousands of wires were spun back and forth across the strait, then compressed into a single cable. The achievement was not only the amount of steel, it was the disciplined transfer of force, repeated across millions of connections. The bridge's apparent stillness is another illusion. Suspension bridges survive by moving. Under changing loads and temperature, the Golden Gate can rise, fall, and shift sideways within designed limits. Official figures describe a maximum transverse movement at midspan of nearly 28 feet, or about 8.4 meters, and a total vertical range of more than 16 feet, or roughly 5 meters. These are design envelopes, not ordinary motion. But the principle matters. Resilience is not the refusal to bend. It is the ability to move without losing the path back to equilibrium. Strauss imposed safety rules that were unusual for major bridge work of the period. Workers used hard hats, respirators, glare-free goggles, and safety lines. A hospital operated near the site. Most famously, a net was suspended beneath part of the span. 19 men who fell into it survived, and later became known as the Halfway to Hell Club. The system did not remove danger. and it should not be romanticized, but it challenged the older idea that death was an unavoidable price of building high above water. Safety became part of engineering, not merely an individual worker's responsibility. 11 workers died during construction. 10 of those deaths came on February 17, 1937, only months before the opening, when a scaffold broke loose and fell through the safety net. The disaster exposed the limit of every precaution. A system can reduce risk without abolishing it. The men who died were not symbols placed beneath an achievement. They were workers whose lives ended while the bridge was nearing completion. Any honest account of the Golden Gate must hold both truths together. The project advanced construction safety, and its completion still carried a human cost. By late 1936, the two halves of the suspended structure approached each other over the center of the strait. They were joined on November 18th. Roadway construction followed through the spring of 1937. At completion, the 4,200-foot main span was the longest suspension span in the world. Yet the lasting achievement was not a record alone. Records eventually fall. The deeper success was that a bridge once dismissed as impractical had become a functioning public route. Completed within the financial framework voters had authorized and ready to change movement around the northern edge of San Francisco Bay. On May 27, 1937, the bridge opened first to pedestrians. Contemporary estimates placed the crowd at roughly 180,000, with some official accounts suggesting as many as 200,000. The next day, automobiles began crossing. President Franklin D. Roosevelt marked the opening from Washington by telegraph signal. For a nation still living through depression, the bridge offered a rare image of public confidence. It did not end unemployment, and it did not solve the crisis, but it showed that long planning, public finance, skilled labor, and shared infrastructure could still produce something visibly larger than fear. In the decades that followed, the Golden Gate moved from engineering news into personal memory. It became an arrival point on a California journey, a background in holiday photographs, a landmark glimpsed from a car window, and an image repeated on calendars, postcards, television, and film. For people who first encountered it in the post-war years, the bridge belonged to an age of road maps, toll booths, family sedans, and destinations reached without a screen giving every turn. Nostalgia softened the structure into a familiar friend. Daily use made it something more demanding. Public infrastructure. That transition from spectacle to routine may be the bridge's greatest success. Today, it serves up to 40 million vehicle crossings a year. Commuters, buses, service vehicles, visitors, cyclists, and pedestrians use a structure designed before commercial jet travel and modern freeways reshaped the region. The bridge helped integrate Marin County more closely with San Francisco, but it also became part of a wider transportation system that includes buses and ferries. An icon can be admired from a distance. Infrastructure must work on an ordinary Tuesday, in traffic, under inspection, with no applause. One of the most persistent stories says the bridge is painted from one end to the other, and when crews finish, they immediately begin again. The truth is less tidy and more revealing. Painting is continuous, but it is prioritized according to inspection and need. The coating protects steel from corrosion in salt-laden air. Beginning in 1968, crews undertook a long program to remove the original lead-based system and replace it with modern protective coatings. That process was completed in 1995. The orange color is not cosmetic nostalgia. It is part of a working defense against decay. Maintenance has repeatedly changed the bridge while preserving its silhouette. By 1986, the original reinforced concrete roadway deck had been replaced with a lighter steel deck system, reducing the structure's weight by more than 12,000 tons. Expansion joints, cables, electrical systems, pavement, railings, and structural members have all required attention. The public often treats authenticity as untouched material. A bridge cannot. If every original component were preserved forever, deterioration would eventually destroy the whole. The Golden Gate remains recognizable because engineers accept a difficult truth. Continuity sometimes requires replacement. The 1989 Loma Prieta earthquake caused no observed damage to the Golden Gate Bridge. That apparent success could have encouraged complacency. Instead, the earthquake became a warning. Studies concluded that a powerful quake centered near the bridge could cause severe damage and close the crossing for an extended period. Vulnerable approach structures faced even greater danger. The lesson was uncomfortable. Surviving one earthquake did not prove the bridge was ready for the next. Historical prestige offered no protection. The same structure that represented permanence had to be examined as a system with weaknesses. A multi-phase seismic retrofit followed. Engineers strengthened approach viaducts, anchorages, pylons, and the Fort Point Arch while trying to preserve the bridge's historic character and keep traffic moving. The final program, listed by the Bridge District for 2026 through 2036, turns to the main suspension span, towers, South Pier, and fender. Plans include reinforcing floor beams, replacing expansion joints for three-dimensional movement, and installing energy dissipation devices. The objective is not to make the bridge immovable. It is to control how forces travel through it when the ground does not remain still. This work changes what preservation means. The goal is not to freeze 1937. It is to carry the design forward without pretending its original details are sufficient for every modern risk. New steel can sit behind historic surfaces. Energy absorbers can alter the bridge's response while leaving its profile familiar. Computer models can test forces that Ellis and his colleagues calculated by hand. Each generation adds knowledge the first builders did not possess. Respect for the past is not blind obedience to it. Sometimes the most faithful act is to strengthen what history left vulnerable. The bridge also carries a history that postcards rarely showed. For decades, it was associated with a devastating number of suicides and with families, first responders, patrol officers, and survivors who pressed for prevention. The subject requires restraint. It is not a dark legend that makes the monument more dramatic. It is a public health failure that continued while arguments over cost, appearance, and responsibility delayed a physical barrier. The bridge's beauty did not reduce that harm. In some debates, protecting the view was treated as more important than changing the structures to protect life. By January 2024, a continuous stainless steel deterrent net extended along both sides of the 1.7-mile span. It sits about 20 feet 6 meters below the sidewalks and reaches 20 feet outward. Official figures reported 8 confirmed suicides at the bridge in 2024, compared with an average of 30 per year during the previous 2 decades. 1 year cannot settle every question of long-term effect, but the early reduction is substantial. The net changes the outline seen from the sidewalks. It also changes the moral meaning of maintenance. Preserving a landmark now includes making it safer for people in crisis. The familiar image remains: orange towers, sweeping cables, a road suspended between city and headlands. But the full story is crowded with people. The postcard leaves out voters who accepted financial risk, engineers whose names received unequal credit, workers protected by new safety practices, workers those practices could not save, painters controlling corrosion, inspectors finding fatigue, and advocates who demanded a life-saving barrier. Nostalgia is strongest when it does not erase them. The bridge can still recall an earlier California without pretending that earlier generations solved every problem they created or inherited. Across Europe and North America, bridges, tunnels, dams, railways, and public buildings from the 20th century are growing old together. The Golden Gate offers no simple formula, but it offers a standard. Build boldly, credit honestly, inspect continuously, replace what cannot be saved, and revise old decisions when evidence shows they are causing harm. Great infrastructure is not proved by the day it opens. It is proved by whether institutions can maintain public trust after the ceremony's end, after the founding generation is gone, and after the risks have changed. The Golden Gate Bridge is remembered as a line across an impossible gap, but the gap was crossed more than once. It was crossed by voters during the Depression, by engineers who turned calculations into steel, by workers who changed expectations of safety, and by later generations willing to rebuild what the opening photographs made look permanent. The orange towers endure because permanence was never assumed. Somewhere on the bridge, inspection, painting, reinforcement, or repair is always continuing. That is not evidence that the masterpiece is failing. It is the work that allows the masterpiece to remain.